Hello, I'm Lee Tangadal, and I'd like to welcome you to this tutorial, the first of the online tutorials which accompany the textbook Operations Management by William Stevenson. In this tutorial, I will be discussing the use of the Excel templates which also accompany that textbook. First, I'd like to comment briefly on setting your player to full screen mode. While you are viewing this tutorial from either the Camtasia or the Windows Media Player, you should set the player to full screen mode by pressing Alt-Enter. This will enable you to view the full Excel page while the tutorial is playing. Then, at any time while the tutorial is playing, you can again press Alt-Enter to exit full screen to have access to the player controls. Second, I would like to comment on setting macro security to medium. This is necessary to enable the macro instructions which are present in each of the Excel templates to be executed. To set macro security, use the command Tools, Macro, Security, and select Medium. Okay, next I'm going to open an Excel template workbook, examine the contents of that workbook, and make a copy of one of the templates in that workbook. This is the workbook for Chapter 5. It contains 4 templates, as well as copies of the examples and the solved problems from the textbook. You can access any one of these worksheets either by selecting the hypertext on this title page, or by selecting the tab at the bottom of each worksheet. The examples worksheet and the solved problems worksheet contain copies of the templates. In order to use those templates, you have to copy the data and paste into the appropriate template. Now let's make a copy of the break-even analysis template. We're going to copy it or tear it out, so to speak, from this workbook and paste it into another open workbook. Right-click on the tab at the bottom of the worksheet, select Move or Copy, check that you're going to make a copy, and we're going to put it into another workbook that's open at the end. Now we have a standalone copy that is different from the original but is functioning the same as the original that we can use for our calculations. Next, using that template, I would like to demonstrate entering data, manipulating parameters, using GoalSeek, and finally printing the template. The example that I'm going to be using is a very simple break-even analysis problem in which we have a fixed cost of $6,000, a variable cost of $2 per unit, and a revenue of $7 per unit. Entering that data into the template, a fixed cost of $6,000, a revenue of $7 per unit, and a variable cost of $2 per unit. Note that you may enter data only in the light blue shaded portion of the template. This gives us a break-even point of 1200. From the graph we can note that the cost function starts at a fixed cost of $6,000 and increases steadily at a rate of $2 per unit produced. The revenue function starts at 0. If you produce 0 units, your revenue is 0. But it increases at a steady rate of $7 per unit, leading to a crossing point at 1200, which of course is the break-even point. The profit function starts at a negative 6,000. Once again, if you produce 0 units, your profit will be negative 6,000, increasing at a steady rate and crossing the x-axis at the break-even point of 1200 units. That answers part A to this problem. We must sell 1,200 pies to break even. Question B, what would the profit or loss be if 1,000 pies are made and sold in a month? To solve that problem using the template, simply enter 1,000 for the number of pies made and sold. Since that point is lower than the break-even point, we would expect a loss as indicated by a profit of negative 1,000, also on the graph by this line segment. Question C, how many pies must be sold to realize a profit of 4,000? To answer that problem using the template, we're going to increase our volume until we achieve a profit of 4,000. This may be facilitated by using an increment of 100, pressing the spinner button, which will increase the volume by 100 each time, and until we achieve a profit of 4,000 at a volume of 2,000 produced. Finally, Part D, if 2,000 pies can be sold and a profit target is 5,000, what price should be charged per pie? In other words, we want to leave the volume at 2,000, but we want to achieve a profit of 5,000. The only way to do that is to increase the revenue per unit. And at this point, we could use trial and error, changing the revenue until we achieve a profit of 5,000. An automated way to carry out trial and error is to use the goal seek. In goal seek, our set cell is our profit. We want to achieve a value or a goal of 5,000 by changing, and our changing cell is our revenue. And goal seek indicates that the necessary revenue will be $7.50. Finally, I would like to illustrate printing this template. You can print the entire template by simply pressing the Print Task button. If you want to append a heading, such as a student name or other information, you can first use the printer preview to set a custom header or footer, typing in the student name or other information that you would like to accompany the printed template. And that concludes tutorial number 1. In tutorial 2, an introduction to Excel, I will be demonstrating some very fundamental concepts in creating and using your own Excel spreadsheet. The example I will be demonstrating is a simple break-even analysis problem taken from Chapter 5. Okay, let me get started by entering some labels. Let me widen that column a little bit, and let's write justify those labels. Next, let me enter the values. The value for fixed cost is $6,000, variable cost is $2, and revenue is $7. Now we're ready to compute the break-even point. Formula for the break-even point is simply 6,000 divided by 7 minus 2, the revenue minus the variable cost. In Excel, that will require a formula, always beginning with an equal sign. And one approach would be to actually type the numbers, 6,000 divided by, in parentheses, 7 minus 2. And that does yield the correct value for the break-even point, but it defeats the purpose of using a spreadsheet. That is, if you have already entered the data, you should reference that data rather than retyping the numbers. Therefore, I will undo that last operation and re-enter the formula by referencing the cells. You can reference the cells either by typing their address or by simply pointing to them, such as 6,000 divided by, in parentheses, 7 minus 2, which again yields a break-even point of 1,200. The advantage, of course, of using cell references is should any of the data change, such as fixed cost, the break-even point will automatically recalculate. That takes care of Part A, determining the break-even point. Now to answer Parts B and C, I'm going to fill in this table. In the table, I'm going to start with units produced, and the table will start with 100 and increment by 100. And Excel conveniently has a fill-in feature by selecting the first two, then grab the handle in the lower right-hand corner and simply drag it down. And let's go through 2,000. Now let's compute total cost. Total cost is fixed cost plus variable cost per unit multiplied by units produced. Now, in order to copy that formula, I'm going to want to make the first two addresses absolute. That is, so they don't change as I copy the formula down. To make an address absolute, I simply select it, either typing $signs or press F4 to insert $signs. That way the first two addresses for fixed cost and variable cost are absolute, while the units produced remains a relative address which will change. And I can simply drag it down. Next, total revenue is revenue per unit, which I will make absolute, multiplied by units produced. And likewise, I will drag that down. Now we'll compute the loss, and loss is going to be computed using an if statement. I can use the Excel paste function task button, and the if statement is a logical function. And it has three parts. The first part is a logical test. So I want to test if there's going to be a loss. The logical test will be if total cost is greater than total revenue. Next is the value if that logical test is true. If that logical test is true, you will have a loss, which is total cost minus total revenue. On the other hand, if that logical test is false, the loss, you will not have a loss, so the loss will be 0. And that will fill in the if function. And once again, if I drag it down, the loss will go away at the break-even point of 1200. Now profit, on the other hand, will also use an if function, and I will simply type it directly. Starting with an equal sign, if, and in this case I will take total revenue is greater than total cost, then we will have a profit. And that profit will be revenue minus cost. Otherwise, our revenue will be 0. Our profit will be 0. And I'll drag that down, and profit will not appear until we pass the break-even point. So now I can quickly answer the next two parts to our problem. First, what profit or loss would be if 1,000 pies were made? At 1,000, we have a loss of 1,000. Since 1,000 is less than the break-even point, you would expect a loss of 1,000. Next, how many pies must be sold to realize a profit of 4,000? Going down, our table just barely made it. We achieve a profit of 4,000 at a volume of 2,000 pies. Now certainly that's kind of an overkill for solving that problem, but it demonstrates in Excel setting up a table. The final question is, if we continue to produce 2,000 pies but target a profit of 5,000, what revenue or what price must be charged per pie? So we want to raise our profit at 2,000 by increasing the revenue per unit. We can either use trial and error at this point, or we could use the tools Goal Seek. And in Goal Seek, we want to set our profit cell to 5,000 by changing our revenue. And Goal Seek will solve finding that the necessary revenue per unit is $7.50. Finally, I would like to demonstrate constructing a graph. First, I will graph total cost. Graphing is simple in Excel. Select the data you want to graph and select the graph wizard. I will construct a line chart, and selecting the Series tab, down at the bottom is a window for category X labels, and I will use the units produced as a category X labels. Next, I will fill in some titles. The chart title will be Break-Even Analysis. The X label will be units produced. And I can simply finish at that point. and I have the chart for break-even analysis. Let's make this line a little bit darker. Right-click on the line, Format Data Series, and just increase the weight a little bit. You will find that Excel creates graphs very quickly, but frequently you have to customize the graphs to your needs. Let me continue by adding the revenue to that. Let me right-click on the existing line, go to Source Data, and return to the Series page. And I'm going to add another series. The series will have a name of total revenue. Well, the values will be the column for total revenue. And it will use the same values for category X labels. And that adds the revenue line to my chart. I can format it by making it a little heavier and maybe changing it to bright red. And you can see that whereas the cost line starts at 6,000 and increases at a steady rate of 2, the revenue line starts at 0 but increases at a faster rate, and of course the crossing point is the break-even analysis. And that concludes tutorial 2. In tutorial 3, forecasting, I will be demonstrating 4 forecasting methods. I will be applying each of these forecasting methods to the same set of historical data, and in hindsight, I will be comparing their accuracy. I have made copies of the templates for each of these forecasting methods, and I have already entered the historical data into each of the templates. Beginning with the moving average method, a moving average with one period is simply the naive forecast. That is, each forecast is equal to the previous period actual data. A 2-period moving average yields a forecast which is simply the average of the previous 2 periods, and so forth. Observing the forecast, the red line, you will see that as the number of periods increases, the degree of smoothing exhibited by the forecast also increases. Comparing the forecast with the actual data, whereas the actual data does have some short-term apparent random fluctuation, the overall pattern exhibited by the actual data is of trend or growth. And the greater degree of smoothing will limit the ability of the forecasting method to react to that long-term growth. Therefore, the most successful moving average forecasting method will very likely be with a very low number of periods and a very low amount of smoothing. Using the mean absolute deviation, that is the mean error, to measure the accuracy of the method, a naive method has a mean absolute deviation of 12.124. A 2-period moving average is slightly better, but the 3-period on up yields successively worse mean absolute deviations. Moving on to exponential smoothing. The exponential smoothing forecast starts out with one naive forecast, and each successive forecast is a weighted average of the previous period's actual data and forecast. That weight is determined by alpha, the smoothing constant. The range of alpha is from 0 to 1. An alpha of 1 results in the naive forecast, and an alpha of 0 results in complete smoothing, that is, the forecast never changes. As alpha is increased from 0 to 1, decreasing the amount of smoothing, we will attempt to minimize the mean absolute deviation. Changing the increment from 1/10 to 1/100th, it appears that the best we can do is a mean absolute deviation of 12.8 when alpha is in the range between 84 and 87. Moving on to linear trend, which is quite a different forecasting method. Linear trend is simply the linear regression equation fit to the original data. whereas linear trend does exactly measure the long-term change, that is, a slope of 6.3441 per period. The linear trend equation is unable to react to short-term fluctuations. The linear trend equation is typically used with other methods which may measure seasonal or cyclical behavior. The last forecasting method hopefully will be the best of both worlds. It will provide a trend which will enable the forecasting method to react to the long-term change while still utilizing exponential smoothing for short-term fluctuations. Trend-adjusted exponential smoothing must be initialized. So let's initialize with a forecast in, let's say, period 5. First, we will compute the trend based on the first and the fourth period. From the first to the fourth period, the actual data grew from 139 to 170. So we will estimate the trend as being 170 minus 139 divided by 3 periods of change, yielding a trend of 10.33. That's our estimate for the long-term change. As you recall from the actual equation, 6.3 is the actual trend. Our forecast for the fifth period will be the actual data from the fourth period plus that trend. So we will initialize the method with a forecast of 180. The successive forecasts are quite complicated, so I will simply demonstrate trying to achieve the lowest mean absolute deviation by adjusting the two smoothing constants. The first smoothing constant alpha is for short-term fluctuations, smoothing, and the second smoothing constant beta is for smoothing the long-term trend for the method. Very quickly, it appears that the optimal we can achieve is a mean absolute deviation of 10.04, which is better than the previous two methods, with a smoothing constant for the short term of 0.7 and the second smoothing constant beta for the trend of 0.2. And that brings us to the end of tutorial number 3.